VCE Chemistry, Unit 3, AOS 2. In this session, we'll look at calculations involving Kc. So, the equilibrium expression and unit is dependent on the reaction written. So, for example, in this case, iron 3 reacting with tin 2 to produce iron 2 and tin 4. How do we write the equilibrium expression for this equation? Remember, the Kc expression is when we put the concentration of the products to the power of its coefficient multiplied together over that of the reactants. So in this case, the Kc should be written in that way. Okay? And remember that for Kc's, there is unit, and the unit is calculated in similar ways. And in this case, that all the units being cancelled out, so there are no units. So when we say that Kc is dependent on an equation, we mean that when we rearrange a chemical equation, for example, when we divide or multiply the coefficient, or when we write the equation in the other way around, Kc expression should also change with that, together with its values. For example, when a reaction is written in this way, NaCl decomposed into NO and chlorine gas, then our Kc is written as products to coefficient over the reactants. And if we are to calculate the value of Kc, then we just substitute what we were given. Kc is calculated to be 0.1 mole. What if we divide the whole equation by 2? In that way, Kc expression should also change with it. Okay? And you can imagine if the expression of Kc changes, because the coefficients are now different, then the value of Kc will also be different. At the same time, the unit for that particular Kc will also change. I know it's a bit weird that the unit is m molar to the power of half, but that's just the way it goes. Okay? On the other hand, what if we write the reverse reaction to be the forward reaction? The equation becomes the product now becomes the reactants, and Kc will also change with it, because Kc is strictly defined as basically whatever is written on the right hand side over whatever is written on the left hand side. And you can imagine the value of Kc will also become the reciprocal of equation A. Okay? So this is what we meant by Kc is dependent. The value of Kc and the expression of Kc are both dependent on how the equation is written. Now, with Kc calculations, there are three major types that we need to know for VCE chemistry. The first type is rather straightforward. Okay? You are given a balanced equation, and you are given the concentrations in one way or another, and you are asked to calculate the value of equilibrium constant for this reaction. Our approach is straightforward too. Okay? First of all, you need to write down the equilibrium expression based on this equation given. At the same time, pay attention to if there is units. Okay. And then the second step is to calculate the concentrations of different substances involved. In this case, the concentration is not directly given by the question, so we need to calculate using mole over volume to calculate the concentrations of three of them. Then the third step will be substituting all the concentrations calculated into the Kc expressions. You notice that I didn't really work out the final value of the three concentrations and just substitute them directly into Kc. If you're very good with operating with fractions, you'd know that if you do it this way, a lot of the numbers can be cancelled out. Okay? But you don't have to. You can just use your calculator to work out the numbers straight away. Okay? When you work out Kc, pay attention to your significant figures. And also, don't forget the unit when there is one. Okay. The second type of calculation is basically the first type working backwards. You are given a constant of a particular equation, then you are given some of the concentrations, but some, and you are asked to find out the concentration of some other substance that are not given. Okay, so our approach is again starting with writing out the equilibrium expression. In this case, we have a unit applied. Okay, and then we substitute the Kc value that's given and the concentrations that are given into this expression. So Kc equals 0.72 and N2O4, the concentration is 0.04. Okay. You probably guessed the third step is to solve this equation for the concentration of NO2. And remember, in chemistry, we are not allowed to use CAS calculator. So you must possess the ability to solve a simple equation. Okay. In this case, NO2 concentration is solved to be 0.17. Yes, you do need to take the square root of NO2 in these steps. Okay. The third type of calculation is quite perplexing sometimes, and that is why we have developed what we call an icebox method to specifically tackle this type of calculation. Let's look at this question first. An equilibrium is established between A and B at a specific temperature, and the balanced equation is A becoming 2B. Okay, so in this experiment, 0.54 mole of A was placed in a 2-liter vessel, and the equilibrium was achieved. And 0.28 mole of B was present at the end at equilibrium. Okay, and we are asked to find the value of the equilibrium constant at this temperature. So I've highlighted the important information from this question. Now let's sort out what the question is telling us. Okay, so basically it's saying initially you have a system that is going to go to reach equilibrium. Okay, so initially you have 0.54 mole of A and 0 mole of B. Then the reaction started. How is the change happening between A and B? We do not know. Okay, but we do know that when the system has reached equilibrium, we don't know how much A was left, but we do know that 0.28 mole of B was left. Okay, so you can see that this table helps us to sort out how the reaction from initial stage and the change and equilibrium. At least we have a clear picture of how the reaction actually goes and what the question is actually telling us. Yeah. So here you have the ice box. Right? But this ice box is rather incomplete. We can do nothing about it. We have to further apply things that we already learned from previous years to make this icebox more complete. And by that I meant we need to use stoichiometry knowledge to make this box more complete. So let's look at this. Initially, we have 0.54 mole of A and 0 mole of B. So as the reaction is going towards equilibrium, how much A was actually used to become B? We don't know. But we do know that actually between A and B, there's kind of like numerical ratio relationship. That is, if you have 1 mole of A converting into B, then we know that there will be 2 moles of B present, yeah, at the end. So since I don't know how much A was converting into B, let's set it as X. So let's say in this process, X moles of A was converted into B. So how much B will be produced then? It will be 2x mole. So at the end, how much A was left in the reaction mixture? It will be initial taking away the change, that is zero point 0.5 mole taking away X. How much of B was left? Initially we have 0 B, but in this reaction, X mole of A is converted to B. So we know that in the end, there will be 2 X mole of B being present. Now this becomes a little bit interesting. We have two tables. One tells us what the data are actually given for this question. The other one is how we, using stoichiometry, to fill out. Okay, do they have some relationships? Of course they do. Look at this. In the end, we know that 0.28 of mole of B was present, and we know that if X moles of A was converted into B, it will be 2X. So these two quantities at the same position of the table must equal to each other. And based on that, we can actually write an equation and solve for X. Okay? So since 0.28 was left in the equilibrium system for B, then 2x must equal to 0.28, and therefore x equals to 0.14. If we solve for x, we are also able to solve how much A was actually left over at equilibrium point. Okay, so since 0.28 mole of B was produced, it must mean that 0.14 mole of A was consumed to produce that. So in the end, there will be 0.54 taking away 0.14 mole of A, which is 0.4 mole of A left. Okay? So now we know at the equilibrium point, 0.28 mole of B was present, and 0.4 mole of A was left over, which is also present. Then we can substitute into the Kc expression and therefore find out the Kc value. Okay? But pay attention that when we used a stoichiometry, we used amount in mole to do the calculations, and we must use amount in mole when we fill out this icebox. Okay. However, before we can calculate Kc, we again need to convert the amount in mole back into the concentration so as to calculate the value of Kc.